Okay, I'd like to introduce our next speaker, Ingolf Steinbach from Jena Optronic GmbH.
Thank you. Good afternoon, and thank you for terminating your lunch break for me. My name is Ingolf Steinbach. I work at Jena Optronic in Germany as a software system engineer for the ASTRO APS star tracker. The ASTRO APS star tracker is a product which comes in several different configurations, and this fact also has quite a lot of impact on the star tracker software embedded in the unit. And today I'm going to talk about how we cope with these flexibility requirements. But before I go into details, let me first give a brief introduction to my company and also star trackers in general. Jena Optronic is located in Germany, some 150 miles to the southwest of Berlin. We do space-based, we provide space-based products, and some of them are sensors which are used in attitude and control systems, or GNC in general, like for instance star trackers, rendezvous and docking sensors, sun sensors, and so on. Another branch of our product deals with optical instruments for Earth observations. And finally, we do software-only projects, like, for instance, processing of satellite data. Our customers are located around the world. So we have customers, for instance, in the US, in Russia, and Asia, and last but not least, also in Europe. On the other hand, our suppliers typically, or many of them, come from nearby. Jena is located in the so-called German Optical Valley, in which several companies dealing with optoelectronics are located. This is due to the fact that several famous people who have done research and development in optics have lived and worked in Jena, like for instance Carl Zeiss or Ernst Abbe. Star trackers, what is their purpose? They are mounted on spacecrafts, look into the sky, take images of the sky image, and then within these images, the star tracker locates star-like objects, like you see here with the red circles. And when it has located these star-like objects, it can then try to find this pattern of stars within an onboard star catalog. And after having this association between the images and the star catalog, which also contains coordinates of these stars, the star tracker is then able to deliver attitude information based on these star measurements to the attitude and orbit control system. So this is, again, the view which the star tracker has of the celestial sphere. And I'm going to talk about the ASTRO APS star tracker, which is our latest flagship product. You can imagine the first star trackers we built, this was in the late 1980s, were quite bulky and had great mass and power consumption. Over the years, this has been decreased significantly. So the star trackers have been smaller and also less power consuming, but at the same time providing much better performance, measurement performance than before. This is our current flagship product, ASTRO APS. APS is the short form for active pixel sensor, the type of detector you also find in state-of-the-art photo cameras. Previously, we had CCD-based sensors. Now this is the first product which uses this technology here. Don't worry, I won't read the complete data sheet to you now. I have a few copies with me, so if you're interested, just talk to me during the conference. And I'm happy to give out these data sheets. Or you can find also this information on our company website. This is just to give you an information or an impression of the size of the unit. It's not meant to be a price tag. So But the Star Tracker itself, the box below is just 5 by 5 inch large. So you can easily grab it with one hand. We don't recommend to do so, but you can just 5-inch this box, and this box contains the complete imaging system consisting of the optical assembly, beneath that the detector, and below that a sophisticated supporting structure. It contains the complete electronics necessary for the data for the Star Tracker to work. This electronics also includes a power converter. So everything is built into this small box here, and you simply have to mount it on the satellite. Well, a bit more is necessary for sure, but mount it on the satellite, plug in the cords, switch it on, and then it starts working. Most of you will confirm that software development in general is quite a fascinating task, but that the most thrilling moment is when you actually launch your unit into space, switch it on, and see whether it does its job. And this point in time, this milestone was reached this year at the 25th of July, when ASTRO APS was launched on board of the AlphaSat, a large telecommunication satellite. It was successfully launched, and we are quite relieved and also a bit proud that it really works like a charm. So let's now come back to the actual software aspects. I already told about our customers that they are distributed around the world, and this is one of the major contributors to the flexibility requirements, because with respect to the operational interface, we have typically very specific demands depending on the region where our customers live. So for sure we have MIL 1553 based communication with the Star Tracker. And even for this type of interface, we provide two alternative variants of higher level protocols. One of them is the ESA PUS, Packet Utilization Standard, which is defined in ECSS and based on CCSS source packets. As you probably know, CCSDS source packets come with a significant amount of overhead with respect to headers and a trailer and so on. So for those applications where we have quite tight bandwidth requirements, we also provide an option with lower bandwidth demands with a protocol designed by ourselves, by Optronic, which in the future I will call JOP protocol. We have RS-422 based UART communication as an alternative space wire, and also some synchronous serial command and data interface for several customers. Another configuration option with impact on the Star Tracker software is the choice of detector. There are currently two space-qualified APS detectors which we can use in the frame of ASTRO APS. The one is the Star 1000 detector, the other the AJS2 detector. Both have different properties, for instance, with respect to radiation tolerance and also with respect to their measurement performance. And finally, also the operating system can be configured not within the actual Star Tracker itself. When we use a real Star Tracker unit, we also always use RTEMS as an operating system, but it's also possible to run the Star Tracker software on Windows or Solaris, so we have support also these operating system below that. So you can imagine we're in a typical supplier situation here, which can be quite challenging. On the one hand, we have the customers with certain demands, for instance, one being that the Star Tracker needs to integrate smoothly into their onboard data handling. And we have to take the various bandwidth limitations into account. there are various scenarios in which the star tracker is to be operated, whether it be a GEO or LEO mission, whether it has high dynamic conditions, and so on. And on the other hand, we have our in-house product manager who wants to have a uniform product. He doesn't like great diversity between the different configurations, and his requirement is that the choice of configuration has only minimum impact on the actual characteristics of the star tracker. And finally, both of these groups have the same requirement that the qualification status of the whole product is to be impacted as low as possible. So when we change configurations from one to a different configuration, this should not require a major requalification of the star tracker software. The first thought that probably each of us has had already in mind was to use this approach called clone and own, where you just make a copy of the whole software and then do the necessary modifications which are to be done to meet the customer requirements. This approach has for sure its benefits and is in certain situations also the right choice, I think, because it's quick. Often you are limited within your time frame. You can easily meet the customer requirements, and this is also because you don't have to take other projects with different configurations into account. But I think it's also necessary to have second thoughts on this approach, at least in some projects, because obviously there are also a few drawbacks of this approach. The first one looks quite similar to the third of the benefits. No other projects are considered. That means you don't provide this consistent characteristics of the product. So the projects will slowly diverge over time. Your heritage is obscured because you just made a copy and then do something completely independent of the rest of the other configurations. And also when you do some improvements in other projects, these improvements cannot easily be transferred to your own configuration. And as you can imagine, this can easily become quite a configuration nightmare if you have several different configurations. So we really had second thoughts on this, and our decision was then to introduce a different approach to this problem. That is the approach of modularization of the software. So what we do here? We used the same core parts in all configurations of the star tracker software. For instance, the algorithms will always be the same code base, identical in all configurations. Our communication protocol stack is also modularized, not only to be exchanged on the whole, one complete protocol stack to be exchanged with a different one, but we have introduced a layering approach which was inspired by the OSI model, Open System Communications. You can exchange different protocol layers with other implementations. And each software configuration that can then decide which implementation of a certain layer is going to be used. Finally, not yet finally, but next point is that we have low-level drivers for those parts which operate directly above the hardware. These low-level drivers provide an abstract interface to upper software layers, so you can implement this abstract interface differently when you exchange your hardware, your underlying hardware. And now finally the operating system abstraction. This allows us also to exchange, for instance, RTIMs with Windows or servers. So let's have a look at the application layer. This is the top layer in the OSI model. The application layer describes the Star Tracker concepts, which we call services. So several of these concepts are the initial acquisition, where we start from a lost in space situation, then try to find the star images and do the identification. Other concept is attitude tracking. Once we have found the first attitude solution and validated it, we can then easily predict where the stars will be in the next Star Tracker cycle and so on. Health monitoring is also such an abstract concept of the Star Tracker. At this layer, we provide definitions of these concepts and also definitions of the parameters which influence the behavior of the Star Tracker. We do not yet define the encoding of the parameters. This is on the next layer. So as I said, this part of the software is identical in all configurations, and by that we can describe the behavior of the Star Tracker, how to use it in a generic user manual. Let's now go to the presentation layer. This presentation layer now is the place where we actually deal with data structures. For instance, it contains the definition of telemetry data blocks and telecommand data blocks. Also, several internal data structures which can be accessed from the outside of the Star Tracker are defined at this layer. And it also includes the definition of the encoding of a parameter. On the application layer, we would just say this is a real number, for instance, and on the presentation layer, we would then define whether it's encoded as a 32-bit floating point or some fixed point notation or something like that. Up to now, we've had just one instance of the presentation layer, so this has been the identical baseline on all configurations, which in some configurations had to be augmented. For instance, in the PUS configuration for ESA, we have added additional services which are required by PUS by itself. But we were able to keep the original data structures of the core functionality here. The presentation layer has its own section with the ICD, which is self-contained, so you can read this section on its own and implement that, for instance, also on the user side. When we go to the session layer, this is the place where the packaging and depackaging comes into play. So for telemetry, we add headers and trailers maybe to the data structures, and when receiving telecommands, the headers and trailers are evaluated. We do sequence counter checks maybe, or integrity checks and completeness checks and so on. We have currently two alternatives of the session layer. One is the low bandwidth implementation, the GOP session layer, which is suitable for any communication media, also for very slow ones. And then we have the other alternative being the POS, which is the CCSDS source packet-based implementation here. This is currently available only for MIL1553 based communication. And again, like in the presentation layer case, the session layer comes with its own self-contained chapter within the ICD. So the transport layer is heavily depending on the underlying communication media which we are going to use. This transportation layer implements serialization or fragmentation when necessary of the telemetry. It reconstructs the telecommands which are received from the outside. It performs handshaking and so on. And we have for MIL 1553, again, two alternatives currently. One is based on the data block transfer, which is defined in ESA or ECSS standard. It consists more or less of a concatenation of all the source packets and then chopping this data stream in pieces of 1 kilobyte each and making that available on the operational interface. The other one is the Jena Optronic approach, which provides random access to your data, so you don't have to configure your telemetry data stream in advance, but you can just ad hoc decide which telemetry data block you want to acquire from the star tracker. And again, this is described in a dedicated part of the ICD. I emphasize this a lot because I think on the user side, this makes also the implementation of his part of the communication a bit easier. So now we can combine all the three remaining layers here. Typically, the functionality required for the network, data link, and physical layer is provided by some controller hardware, which might be augmented by additional software. We implement these drivers for the hardware in our hardware abstraction layer, and as I said, this hardware abstraction layer provides an abstract interface to upper layers. So, for instance, when we deal with MIL 1553 controllers and have two different implementations of controllers, alternative implementation for controllers, we just need to rewrite the driver for the controller and don't need to change anything above that. Everything else can remain the same. So as I said, the abstract interface is not impacted by this exchange. So let's look at a few numbers here, the amount of reuse which is possible when we do this approach. I've showed you here two examples, real-life examples. On the left-hand side, the MIL 1553 configuration with JOP protocol, and on the right-hand side, the UART configuration, again with JOP protocol. And you see everything which is marked in green colors remains completely the same. Has no changes necessary here, and only the small amount at the top, which is colored in blue and orange, needs to be rewritten when you change the operational interface to a different communication media. So what are the benefits? For sure, cleaner design. And also this approach allows us to write stubs for each layer in the protocol stack. This supports quite heavily the development and testing process. So we are easily able to implement tests for the session layer only, for the transport layer only, and these tests can run completely on simulation hardware. We don't need actual simulator software. We don't actually need hardware for these kind of tests. Only for the low-level drivers, this is the first time when hardware in the loop comes into play. And for sure, when we do the integration, we also need at some point in time the hardware, but we can do much of the tests on a complete simulation basis only. For sure, we can easily inject errors at different layers of the communication protocol, and by that, we reach 100% of modified condition and decision coverage. Easily, we do much more tests than would be necessary to reach this 100% measure here. And finally, this approach allows us to provide simulators for the star tracker, which run on completely different environments, like, for instance, Windows, which does the same processing as the actual hardware, the actual star tracker software. From the user point of view, this approach also has a few benefits. One of them being that the qualification status is clear here. So we can, even if we go from one configuration to a different one, we can clearly show the user what needs to be changed, what needs to be requalified. Another benefit is that we have this clear structure within our documentation with one generic user manual and the interface control documents, which are then structured in the way that we have the different layers in separate chapters. And this also aids the development at the user side. It can also implement such a layered approach to the communication, but our approach does not enforce using the same approach at the user side. And for us and the user, we can easily identify which changes are necessary when we change the media. For instance, if the customer has bought type X up to now and now wants to change to a different communication media, we can just clearly show him what needs to be done here. So, to conclude the presentation, for sure our approach has a few drawbacks. One of them being that we need more design effort. When you do this retroactively, you need a certain amount of refactoring when you want to implement such an approach in already existing software, and so in the short-term view, this leads to higher costs. But there are quite a few benefits from this approach. In the mid and long-term view, you can reduce your costs because you can, your amount of reuse is much larger than in other approaches. We have this clean design benefit, and one very important benefit is also that we have really a consistent behavior of the unit, which is not depending on, for instance, the operating system. Others you see here, ideal testing and simulation capabilities, only small delta qualification, which is necessary when changing configuration, and also this quite a significant amount of flexibility. For instance, we can also deliver star trackers, which are not intended for flight, but can be used when you do avionics test bench integration of the star tracker, which comes with different, cheaper hardware. We just need to exchange the hardware drivers here, but from looking at the outside, from the outside of the star tracker will be exactly the same. So thank you very much for your attention. I see we have a few minutes left for questions.
Any questions? Yes, I do. Wait. I hate to be a stickler, but we actually record this. All these show up on YouTube.
So most of the time, the star tracker is used for space vehicles, I assume. So how readily does it lend itself to reprogramming if you want to reparameterize its performance?
Pardon? Could you rephrase it? I didn't understand it.
If you configure the software a lot with parameters, and can you do this on orbit?
Do we?
This is a star tracker,
Yeah.
correct? Okay,
Yeah.
and which would be launched on a space vehicle?
Yeah.
And is it possible to reparameterize it once it's on orbit?
Yes, for sure. The software itself is stored on ESquareProm, so we can exchange the software. We have also a fallback software which is stored on PROM, so if anything goes wrong during the reprogramming, you can then use this fallback software and do the reprogramming again. And also the parameters, the complete star catalog, and so on is all stored on ESquareProm, so you can exchange, update your parameters once you're in orbit.
Okay, and the second question,
I've heard stories of star trackers, and I don't know who the manufacturer was, that on a satellite that experienced inertial failure, which was the primary gyroscopic way of activity, falling back to the star tracker, which actually did quite a good job. Is that anything that your company has had experience with?
Yes, for sure. There are instances of star trackers which fail, and what we're
Well, this is a gyro that failed, and the
Okay,
star tracker took over.
Yeah. And what was your question?
Well, I was just wondering, I don't know who the manufacturer of that particular star tracker was.
Yeah.
I guess I was asking, was that your company?
We have had failures in the past, not with ASTRO APS. It's just in space for a few months now. We have learned quite a few things out of these failures and have taken these also into account when redesigning.
Oh, yeah, okay, that's a great. I didn't mean to inquire if about your company's failures. It was a serendipitous, a lucky thing that the star tracker was situated such that it could take over, at least on a temporary basis, for a failed gyroscope, and that was
Yes.
it. Apparently.
I think you need at least, or you should probably need at least 2 or 3 of them when you really want to replace a gyroscope there. So, but this is also a typical configuration on the satellite, that you don't just fly with just one star tracker. And it also depends on the update rate, whether the star tracker is capable of replacing a gyro, I think. So we typically do currently with 10 Hertz update rate. We have projects which do 16 Hertz update rate. And then you're in a frame where sooner or later you can completely replace the gyro by star tracker only approach.
All right, thank you.
Any other questions? Yes. Oh, of course.
Gotta get your
You guys are gonna sit in my question order.
So is this limited to use in spacecraft? I mean, could you actually use yours, with an atmosphere in between the star tracker and the stars?
Depends on your measurement performance requirements. We do real sky tests on ground with a star tracker, which has quite a lot of atmosphere in between. It's certainly not useful for scenarios in which you're flying through the atmosphere and need very accurate pointing there, because you have, due to distortion effects and something like that, you have disturbance of the attitude measurement, but it does not render the attitude measurement completely impossible to have the atmosphere.
And what about sort of noise rejection, in the sense of like if you had a lens over top, and that lens was getting crud on it of various sorts?
Yes,
in my case, it would be crystallized salt.
Yes, this is a typical thing which is analyzed during our worst case analysis phase, when we have customers with new missions, and so they typically will provide some information about the environmental situation in which they are going to operate the star tracker, and the contamination of lenses is also one of the points which are assessed by us. And there are also some measures within the software which try to reduce the impact of such contamination on the attitude measurement performance. But more or less, it's a thing that is evaluated on just worst case analysis basis, and then you can decide whether you need to implement some different measures to reduce the amount of contamination here.
I just had a question on whether you supported Linux. I see you have Windows and Solaris, and if you supported Linux. That was my only question.
In theory, we can also support Linux. Up to now, we didn't have any customer which wanted to have a Linux-based solution, but I don't see any argument against providing a Linux solution.
Okay. Any other questions? No? Okay, thank you.
You're welcome.